Part the third. Right. So I think someone mentioned it. What happens if you have large word sizes, what we'd like to have, right? Word sizes like log n, but the symbols that come in are binary. Now, if you just plug in our result, you get something like log n over w, so if delta equals 1. And if w is log n, then you get a lower bound of constant, which is utterly useless. So our results don't seem to give anything even vaguely interesting in what I regard as a very interesting case, right? You have a binary input, one symbol, let's make it concrete. A bit comes at a time, your vector is a bit vector, and you will now put the inner product between your vector and the last n bit substring or subvector of your stream. Right? The question is, can you do some sort of bit backing trick in order to make that very quick, or is that going to be slow like it was when the alphabet sizes were large? Right, well, we get no immediate answer to that question just by plugging in the values delta equals 1 and w equals log n. But there are reasons to believe that maybe we should be able to get something interesting out of it. So imagine the output is in some range 0 to n, which exactly it is in the convolution case, right? Each output is a number between 0 and n. It's the inner product. Right? Then the total entropy over n over log n outputs, so not n outputs anymore, could be linear. Because the entropy of one output could be like log n, and there are n over log n outputs, so it could be linear. And were it linear, then we could, in fact we have developed a kind of a modification of the information transfer technique, which we call the lopsided information transfer technique, with homage to Mihai Petrescu, it's lopsided distointness, which would then enable us to show good lower bounds, the sort of lower bounds we want. Of course, is this actually possible? Second line, well, that's the big question which we'll try and address and ask as well. So here is a specific problem for which we can actually, the statement is actually true. And this is the problem known as pattern matching with address errors. This is meant to be a telephone operator who's not very good at plugging in the right cables. People want to communicate with each other. But the general idea of pattern matching address errors is that standard pattern matching historically is interested in sort of noise in the pattern where symbols get changed to other symbols. And you want to find whether two patterns are within some distance under noise. Right? In pattern matching under address errors, we imagine the noise is not in the content, but is in the addresses. So in other words, just symbol 5 a symbol 5 is actually put at symbol 10 by mistake instead. The operator has plugged the wrong cable in somewhere. Right? So this is a studied problem, pattern matching under address errors, and we have an example here. Imagine that, for example, the message you want to send is 11 plus 2. So the string 11 plus 2. And the operator mucks it up, and you get errors in your addresses, and instead you receive 12 plus 1. If you look at it, you will notice that 12 plus 1 is an anagram of 11 plus 2. This T got moved over there, that W got moved over there, this E got moved over there, that L got moved over there, for example. In this case, nothing terrible happened, but in general it could be obviously quite unfortunate. So what's called pattern matching address errors has a slightly complicated name for the distance function, the L2 rearrangement distance. I prefer just to call it the anagram distance. But you can define a distance between two anagrams as simply being the sum of the square of the distances between the indexes of the symbol in one, index of the symbol of the other, where pi is the permutation here. So you assume the two things are actually permutations of each other. If they're not permutations, the distance is infinite. And offline, Amir and others published a paper which takes n log n time to compute this L2 rearrangement distance for every alignment of the pattern in the text. And online, using a modification and reduction I described before, done with Ben Sach, we can change that to log squared time. So it doesn't, our previous online to offline reduction doesn't work directly, but with some more work you can make it work. So we have a log squared upper bound for this. So to make it concrete, let's imagine that we had two strings, 11100 and 10110. The L2 rearrangement distance is going to be, well, the first one just stays where it is. The second one has to move 1, so we get 1 squared distance The third one has to move 1 as well. This 0 has to move 2, has to move back 2, this 0. And this last one stays here. So we get an L2 rearrangement distance of 6. Right. So if we want to compute the L2 rearrangement distance between a pattern and every substring of the right length of the text, then it's n log n time offline and online log squared n per new symbol. This problem is going to turn out to work out very well for us in trying to prove a lower bound for binary inputs with large word sizes. Is everyone clear what the problem is? Okay. Right. So our new lower bound for binary inputs and large word sizes is going to be log squared n over w times log n. In order to do this, we're going to have to construct some random input distribution so the conditional entropy of the outputs is high, as before. And remember, it really has to be very high. Right? We really have to exploit that every output is going to give us like log n bits of information. Because the L2 rearrangement distance is some number with potentially log n bits of information in it. And we also have to somehow replace the information transfer tree which we had before by something a bit more sophisticated, because we're going to have intervals of non-symmetric lengths. Previously we looked at the information transferred from an interval of length L to another interval of length L, but now there's going to be a log difference between the length of the output interval and the input interval in some sense. Right. So how do we do that? Well, more or less we do it like this. So we're going to look at the first interval, which is going to be the unknown interval in our previous picture. It's going to be of length L log L. Right? And the second interval, which is going to be the interval of the outputs we look at, is going to be of length L, so there's a log factor difference. But we can't just plug that into a tree, because what would happen is we'd start double counting. Right? The whole no double counting thing would fall apart. So what we do instead is we make a little gap between the two. And so at one level of the tree, everything would be fine. The problem is that you don't want to double count between one level and the level above. Right? And this gap is going to have the nice feature that we're never going to have the case where we count the same transfer information from here to here twice. Well, and basically, fundamentally, well, the most interesting feature of it is that the entirety of the first interval is going to sit inside the gap of the level above. So remember, these levels go up, they get bigger and bigger and bigger, the intervals, as you go towards the root. Eventually the root is the whole input's the interval. Right? So if we can compare a node at one level with a node above it level, the whole of this thing is going to sit inside there. Right? And there's some other cases, but that's the most fun case, one might say. And we're going to need to go up by factors of log squared and only start at n cube root of n and various things like this, which is why we lose a log factor eventually. But that's the basic idea. To get this lopsided information transfer to work is this gap. Right. And the upper bound we're going to end up with, the entropy of our outputs, given the fixed stuff is fixed, is going to be very similar form to we had before, but now we're going to have the information transfer from the first interval to the second interval, plus the information transfer that fell down the gap. Right? We're here, and we have to reason about this falling down the gap information transfer. So, and what we managed to show is for the L2 rearrangement distance, there exists a hard input distribution such that the entropy of the outputs is greater than or equal to some constant times L log n for any fixed inputs. So that's the general idea that's going on. And this is a guy here trying to avoid falling down the gap. You notice he does lose some of his information down the gap, but doesn't lose too much. The briefcase makes it to the other side. And that's what we have to argue about as well in our case. Although clearly some information get transferred down the gap, we don't want it to be too much. Because we want to show a lower bound of the amount of stuff that makes it to the other side. So again, we remove the conditioning by taking expectations over the fixed stuff. Well, and we get the expected information transfer. It's going to be at least as big as this value here, L log n over W minus the stuff that falls down the gap. And then we're going to have to sum very carefully, right, over make sure which particular left and right intervals we take into account. We're going to have to choose this as a subset. It's a whole lot of work that goes on. But eventually we end up with this log n log squared over W if we choose those correctly. So basically there's a bit of work that has to go on in order to replace the information transfer tree by something that works a bit better. But let's just give you one slide to try and give you an indication of what the hard distribution is going to be. That's perhaps more interesting than the technicalities of exactly how we make this lopsided information transfer to work. So the stream itself is nice and simple. The stream is just going to be successive 4-bit blocks. And a 4-bit block can either be 0101 or 1010. We're going to choose those 50% probability of each. Okay. So the stream is nice and simple. The text, on the other hand, is not so simple. But the text is going to be structured with the following properties. So this is an output, 1001. And remember, what we want is the output to give us log n bits of information. And this stream, which is now called U, this is the stream, and this is our fixed pattern. Okay. So what we'd like, well, what we're going to ensure is that from any given output, each bit of the output is going to tell us one of the 4-bit blocks in the stream. That's the idea. And the way we're going to achieve that is by structuring this pattern in such a way that, well, we want to make sure the contributions don't interact with each other in some very awkward way. It would help if I had another picture here. Maybe I can draw another picture. So these x's are repeated stretches of 1001s, which is not very interesting. It's the interesting stuff that happens in here. And these look like 1, 0, 0, 0, and then and then 1, 1, 1, 1, 1, 1, 1, 1, 1, and then some zeros. And the number of zeros here, we need to have the same number of ones and zeros, otherwise our distance is going to be infinity. Right? And the number of zeros here is going to be varied by power of 2s in order to make sure that we select the different blocks in here. Anyway, the basic point would have helped with another picture. But anyway, the basic point is that by carefully structuring this thing, we can make sure that the individual bits of the output are going to tell us individual 4-bit blocks of the stream. That's the idea of everything, which will ensure that we get the right entropy. So that's sort of a very brief picture with a picture missing of the L2 rearrangement distance. So that works out very well. But the question is, can we do this for some other problem? This had a very particular structure, this L2 rearrangement distance. Is there another problem that we can do this for? And this is where we get into the really sort of open problem areas. So what about convolution? What inner product? Is there some way of performing a similar trick? Well, what is the entropy of n over log n consecutive overlapping inner products? Right? So if I give you have random 0, 1 text t, let's say, or let's call it stream S, let's say, and I give you inner products n over log n different inner products between some fixed thing b and different substrings of the stream. Right. What's the entropy? If this is uniform random binary, for example, what's the entropy? That question turns out to be difficult to resolve. But we can have a go at seeing what we think about it. What we'd like, of course, the entropy to be linear. So, first of all, let's make sure we understand what, if you remember from the previous picture, from a previous hour, consecutive overlapping substrings of the same length of a stream look like rows of a Toeplitz matrix. You remember? Okay. So this is the same as asking what the entropy is of the product of the Toeplitz matrix and this vector v. Okay. So over here, for example, imagine we have this substring length 4, so the bottom row is the first 4 bits, then it's bits 2 to 5 and 3 to 6 up there, indexing from 1. This is a Toeplitz matrix. If you look at it, the falling diagonals are all constant. Okay. What we'd like to know, and the fundamental conjecture is, what is the entropy of an L log L by L Toeplitz matrix multiplied by a random matrix, random vector x? If that's linear, then we could plug it into our lopsided information transfer technique and get the lower bound that we want. But to phrase it, to make it clearly, do there exist Toeplitz matrices of those dimensions so the entropy of mx is linear? Straightforward mathematical question.
So the Toeplitz matrix is binary?
Yes.
Toeplitz matrix?
Everything's binary.
Right.
All over the reals. All operations over the reals.
And so the output is a number, is this number between
0 and n. Exactly.
0 and
N. Yeah, whatever, yeah.
L.
Yeah, L in that case, yes. Exactly right. Do there exist Toeplitz L log L by L matrices so the entropy of mx is linear in L? It's a maths question, which it turns out not to fall within the current realm of knowledge of mathematics. But a related question has been studied, and it's quite a fun question. It's a coin weighing question. It's a fun question to ask any smart students you know. So imagine that this was posed, I think, in American Mathematical Monthly in the 1960s, possibly even before somewhere. All good questions in mathematics were posed originally as puzzles in American Mathematical Monthly, as far as I can tell. So you have n coins, some of which are real and some are fake. And the real ones weigh 1, the fake ones are really very fake, they weigh 0. And you have one, what they call spring scale. It's just a weighing device. And let's say the coins are numbered. And you can put subsets of the coins on your spring scale, and it gives you a number, right? So you put them all on, for example, you know exactly how many are real immediately. Right? And you want to determine precisely which coins are real, which ones are fake. And the question is, how many weighings do you need to do this in the worst case? So a moment's thought, if I'd given you a moment's thought, would tell you that you need at least n over log n weighings, because every weighing is a number between 0 and n, the log n bits of information. In the end, you need to label all these coins, whether they're real or fake or not. So you need n bits of information at the end of it, so you need at least n over log n weighings. So that's the lower bound. We see that, for example, with 4 coins, 3 weighings suffice. This is a weighing protocol, so what does this matrix mean? It means in the first weighing include coins 1, 3, and 4. In the second weighing I'll include coins 1, 2, and 4, and then coins 1, 2, 3 in the third weighing. And just those 3 weighings will be able to tell me that exactly what the answer is. And so you can just sort of check it mathematically for yourself, that we know that we get that just by looking at linear equations, we get that x1 plus 2x2 is e2 plus e3 minus e1. And x1 plus 2x2 is a very useful thing for us, because if we know what it is, we know exactly what x1 and x2 are. It uniquely determines x1 and x2. And then that immediately uniquely determines x3 and x4. Okay. Right. So just you need 3 weighings for 4 coins. Okay. Another way of looking at that is we could have just multiplied this matrix by this full matrix here, where the columns cover all possible binary vectors of length 4. This matrix probably has a name. Anyone know the name of a matrix of this form? I don't know what it's called. Okay. Anyway. Sorry?
Does it have a name?
It probably has a name. The matrix, we have all possible columns.
So I mean, this usually...
The IHP matrix.
Yeah, so, right. Well, there's a standard name.
IHP, IHP.
Oh, for here.
Yeah,
for
exactly, yes.
Oh, okay.
Yeah, okay. Right, anyway, multiply this matrix here.
It's shattered. It's the shattered matrix.
Shattered?
Well, you know, so if you have a bunch of properties of a set, so if you have a sufficiently, you get all possible subsets.
Oh, okay.
A subset of variables.
Okay.
DC-dimensionally.
Okay, great, thank you. Anyway, you could just multiply the matrix by here and observe that all the columns are distinct. So what we require for this to be able to tell you exactly which coins are free, fake, and which one is that all the columns of this product are distinct. Okay, that's another way of looking at it. And if we stare at them, we can see they're all distinct. Right. So this uniquely determines the labelings of the whether they're fake or real for the coins. Okay. Now it turns out that with 12 coins, 7 weighings suffice. And Erdos and Henri in the 60s showed that in fact it's not n over log n low bound, the real low bound is 2n over log n. And this 2 looks like magic until you, but I have a very kind of hand-wavy heuristic that convinces you, I think, in 2 seconds why it should be a 2. In that I told you the values are between 0 and n. Of course, we all know in reality that almost all values are going to be somewhere near the mean plus or minus square root of n. And then, of course, log of that range is log n over 2, which is why you need this 2 factor in there. Right? Of course, one can do the mathematics properly, as Erdos and Henri did, but just in a very hand-wavy sense, that's where the 2 comes from. Right. So, and they have, right, and then Lindström in 64, 65, and then others showed explicit protocols. And it's a really difficult puzzle. It's sort of elementary but difficult puzzle to come up with an explicit protocol for this problem. And I say, if you have any very smart students who like difficult puzzles, there's no maths in it, it's just a tricky puzzle. And to come up with an explicit protocol. And it's fun and tricky. And if you read Lindström's paper, he quite literally says, we solved the 7 by 12 and then stared at it and saw a pattern. So having seen the pattern, they were able, it's not there, is it, to in fact, give it solutions which are asymptotic to 2n over log n. Okay. So the lower bound and upper bound are now the same, to within, well, asymptotically they're the same. So that's rather nice. I'll try to get some hint of the solution there by the way I've collected the columns together, but anyway, right. But in our case, of course, we need things to be turtlets. So let's just carry on with that non-turtlets problem, the general coin weighing problem. And so what's a really straight, simple, quick way of convincing ourselves that it can really be solved in order n over log n by matrices, right? Order n over n over log n weighings. Well, here's the simplest way that I know about. So you want to prove the existence of a matrix M so there don't exist x and y, so in other words, labelings of fake and real coins, with x different from y, so that mx equals my. Because if they did, then there'd be 2 different labelings you couldn't tell apart. Right? This is exactly the same as saying if there doesn't exist a non-zero vector of length n of -1, 0, 1, so that mv equals 0. And all I've done here is I've subtracted my from both sides, nothing else, right? And observed that x minus y is now a -1, 0, 1 vector. Right? That's all that happened. Just literally subtracted x from y. Okay? So what we can do now is we can just sample our matrix uniformly at random and look at the probability that the matrix doesn't solve the problem. So a matrix that solves the coin problem, is called detecting. So you want to see the probability it's not detecting. And this is nice and straightforward to do because every row of our matrix is independent. Right? So, and what we do is we fix the number of 1s and -1s in V, fix it to some value. Right? I think in this value it's going to be the number of k's, I think, is probably, the number of 1s is probably k, in fact. Right, the number of 1s is w. And we just fix it to something, and then once we've fixed it, the probability that an inner product between a random 0, 1 matrix vector and a vector with a fixed number of 1s and -1s can be written down explicitly. It's this term over here. It's just basically you do a symmetric random walk, probably back at the origin. Okay, right? And then we want to know, we can just take the product over all the rows, and then we have to sum over the different possibilities of 1s and -1s. Right, so we get this sum here. So it's nice and straightforward to write down. Now, of course, this is an upper bound because I've taken the sums, right, and so I've done union bound effectively to get upper bound. So you might worry that's not good enough. But anyway, there it is. Yeah.
So this is the
No, this is a new thing.
Oh, this is a new thing. Okay.
Yeah, it's just it's elementary. I mean, it's not new. It's not new in any interesting sense. Henri already did it beautifully. This is just a more elementary way of writing it down. Yeah, yeah. They dealt with -1, 1 matrices. We deal with 0, 1 matrices. You know, who cares? But it actually does make a difference in a second. Right, so how do you get, so this upper bound, we want to upper bound this upper bound. So how do we do that? Well, the easy way to do it is to pull up magic inequalities. So there are two, one which we all know, n choose k is less than or equal to ne over k to the k. This magic inequality we don't all know, but it's it's basically in Concrete Mathematics, wonderful textbook by Knuth and others. And if you plug in these magic inequalities into this and turn the handle, you will find that we have an upper bound of 1 over the square root of n plus 1 times 2 over pi to the m over 2 plus the sum of 2ne to the w over w to the m over 2 w to the w. This is a much nicer object to play with than the previous objects, because it hasn't got any tricky binomial coefficients or anything in it. So we can then just see that if we plugged in m is 4n over natural log of n, then this thing converges, this thing tends to 0 as n tends to infinity. So the probability of being not detecting tends to 0 as n tends to infinity if you have this many rows. Now you'll notice this numbers are wrong. The 4's wrong. I've got natural log. It should have been base 2 log. I don't know how to get the correct constants out of this elementary method. Interestingly, if we did the same maths with a -1, 1 matrix rather than a 0, 1 matrix, you get exactly the right constant of 2 plus epsilon. But with 0, 1 you don't. Presumably why Erdős and Renyi analyze the -1, 1 case and not the 0, 1 case, I assume. So the probabilistic method somehow doesn't give you a tight constant that the explicit protocol of Lindström does. But up to constants, it's all fine. Right? And it's nice and straightforward, basically. As long as you have a copy of Concrete Mathematics to hand, it's all nice and straightforward. Thank you, Knuth. Right. However, back to our problem. We require the matrix to be turplets. So this is all open problems from now on. Don't expect anything solved from here until the end. Okay. And this is a problem, because I don't know how to apply this probabilistic method to the turplets matrices. I don't know how to reason about the probability that a turplets matrix is not detecting, because the rows are not independent of each other. And that was crucial to get that nice combinatorial sum. I don't know how to make an explicit protocol. I have stared at the 7×12 solution and tried to see a pattern like Lindström did, but I didn't get enlightenment. A better puzzle solver than me might be able to do it. But let's look at some solutions just for fun. So with four coins, there exists a 3×4 turplets matrix that is detecting, which is the same number as we had for non-turplets. For 5 coins, there exists a 4×5 turplets matrix. You will see this matrix here, which is detecting, which is the same number as we had for non-turplets, right? There are many fewer turplets matrices than non-turplets matrices. The turplets matrix is defined by its first row and its first column, whereas, so the number of different turplet matrices is just 2 to the sum of the number of the size of the row and the column, whereas the number of different matrices in general is 2 times the product, 2 to the product of the number of rows and columns. Right? It's a very, very different number to each other. But nonetheless, there also exists a 4×5 turplets matrix that is detecting. If you have 5 rows, then there exists a turplets, 7 coins, there exists a 5-weighing protocol, 5-row protocol, that's turplets, which is exactly the same as the optimal number for the non-turplets case. If I have 12 coins, then there exists a 7×12 turplet solution, which is exactly the same as the non-turplets case. 6. Is that 6? That must be 7 then. That was 6×9? 6×9, 7×12. Right. And in general, if you compute it, if you fix the number of rows and maximize the number of columns, for the general case, non-turplets, the maximum number of columns for which there exists a detecting matrix is 2, 4, 5, 7, 9, 12, 14, 16, and probably 19. My computer got tired. And in the turplets case, it's 2, 4, 5, 7, 9, 12, 14, 16, and probably 19. There appears to be no difference at all between the turplets case and the general case, as far as small examples can tell us.
And you only need a constant factor.
I don't even, so A and B, we don't need the thing to be detecting, right? In detecting matrix gives you exactly linear entropy, but n over 1,000 entropy will be fine, which is a lot less. If you think about how entropy works, that's considerably less. So we don't need this very strong requirement whatsoever. So here's a mathematical conjecture. So a dissociated subset of the vectors, 0, 1 vectors in the reals, is one that has exactly the property there are no two subsets. There are no two subsets of these subsets that sum to the same value, which is the same property we had, which is exactly the same as saying the matrix. If you imagine these subsets are vectors of a matrix, to say the matrix is detecting. That's basically the reformulation in terms of -1, 0, 1 vectors. It's the same thing. So the largest size of a dissociated subset of the set 0, 1 to the n, with the additional restriction, there is some way of arranging the vectors in it as columns of a Toeplitz matrix. Our conjecture is half 1 plus little over 1 n log n, which is exactly the same as the conjecture without the restriction to Toeplitz. Okay. That's conjecture, mathematical conjecture number 1. But we don't need, as you say, completely detecting matrices. We only require that the entropy is linear in n, not exactly n. So the question is, do those things exist? Which is a much weaker conjecture. So let's have one last go at seeing if we can make sense of this thing with maybe some more interesting numerical experiments. So if you remember, we formulated our problem in terms of the question of whether there exists a matrix M so that MV equals 0, where V was a -1, 0, 1, V was a -1, 0, 1 vector. Okay. But let's just for try and understand the mathematics, remove the zeros entirely, just to have a look at the entropy of M, Y, where Y is a -1, 1 vector instead. Okay. And let's go back slightly to our original formulation over there. So we have this thing is here is what I've called F. This is F over there. And we're going to look at the cross-correlation, which we define here. Just this, so each one of these terms is just an inner product, and they're just the shifted inner products. So as you shift along. Okay. And we're going to let S be some random vector, -1 vector. And we let, with probability of half each way, and when F in our full version should be a random -1, 0, 1, sorry, that should be a 1, -1, 0, 1 vector, with the probability F is -1, should be the probability F is 1, which is a quarter, and this is 0. That's because there's difference between, all I've taken is two random 0, 1 vectors and subtracted them from each other, x minus y, so that you're more likely to have a 0 than you are to have a 1 or -1. Okay, that's all that's happening there. So this conjecture here says that for the correct setting of the parameters, that the probability that all these inner products are 0, all the consecutive inner products are 0, is exponentially small. So this is equivalent to our entropy conjecture. Well, in particular, if this is true, then the entropy conjecture is definitely true. So this is nice and straightforward. We're just asking, what is the probability that lots of consecutive inner products are 0? Right? Is it 2 to the minus omega n? So that's equivalent to our entropy conjecture. Now, as we said, let's just get rid of the zeros for a second and see if we can draw a picture. So what I've done here is I've done exactly the same previous formulation. Now F is just as -1, 1, everything's just -1, 1 now. Okay. And what I've done is I've computed the value AI, where AI, is it defined on the screen? It is. Right, AI is the ith inner product, so there are different inner products, right? And we've computed the probability that AI equals 0, given that all the AJs are 0 previously. So what's the probability that the ith inner product is 0, given all the inner products before are 0? Now, if they were really independent, each one of these inner products would be like 1 over the square root of n, or constant over the square root of n, which is the asymptotic probability that this inner product is 0. Just the probability of random walk goes back to the origin. Okay. And if they were really like square root of n, then if we had n over log n of them, then we would have what we wanted, right? Okay. Okay. So the question is, what do they actually look like? So you can compute it numerically. So n has to be even because I've got rid of the zeros, otherwise the inner product can't be 0, right? And I have n from 12 to 22 here. And this is this probability here. Right. And so the probability that AI equals 0, given all the previous ones are 0, you see is more or less flat. Right. Until at some point when it goes up quite quickly, and then it's more or less flat. And what we require is to know how large the flat region is. Because where it's flat, then it acts like they're basically independent. And up here, they're sort of dramatically dependent, and there's a mysterious transition in the middle. But this picture in particular, when I drew it, probably 2 years ago or something, is the first thing that really convinced me that the conjecture is very likely to be true, I have to say. Because there's this flat region, and we only need this flat region to be like n over log n in size. Well, in this case, n is 22, so n over 2 is sort of here. Yeah, this is the 22 line, right? We only actually require it to be flat for a little bit. Now, since this time, we've done a lot of investigations, and there are many other sort of heuristic reasons to believe the conjectures are true. In fact, I would now bet money the conjecture is true. But we haven't managed to solve it, unfortunately. Any thoughts on that would be really great. So that was... Right. So you might ask, well, what is known? Well, the first conjecture I said was that the large size of the associated subsets with this internal restriction is like n over log n, but in fact, we don't know anything bigger than n at all. But I don't think we even know 2n. Right? So that's quite surprising. We can't even give you 2n on that thing. For this second conjecture here, the probabilistic one, where we want it to be the probability that lots of inner products are 0 to be like 2 to the minus omega n. We don't even know for n over log n consecutive inner products, so we don't even know about n over square root of log n or n over 100th root of log n. We don't know about that either. Right. So that really is, I think, a very interesting and quite deep, it turns out, area which involves new mathematics, I now believe. And we also make a very nice step, I think, forward in our understanding of how to prove lower bounds in a case where the existing techniques seem to hit a wall. So here's a final list of open problems, just to finish off the story. All manner of streaming problems which we think are hard have low entropy outputs, and therefore our technique doesn't work. Right? Edit distance with large words. The consecutive outputs are just a constant different from each other. So our technique just falls apart. Sliding window longest common subsequence is the same issue. Consecutive outputs differ by which we're sure they're hard, these problems, right? We're really sure about it. But consecutive outputs differ by only a constant. So we need a kind of technological improvement in order to say something about that. Exact matching with wildcards, right? So exact matching with wildcards is the problem where you add single character wildcards in the pattern or the text, or both, you can choose. And you just want to know where it matches exactly. So offline this is solved by applications of fast Fourier transforms and n log n time. We're pretty sure this problem's hard, log squared online. The technique completely fails because the entropy arguments just don't apply. Basically, the answer is always no. Does it match? No, it doesn't. Yeah. What do we have to say about it? Is there anything we can do to attack that? Now, there are problems for which the answers typically know where we can give lower bounds, but I don't know or see how to apply it here, unless someone in the audience wants to tell me how to do it. Decision versions of our problems, so parity, let's say, for convolution or Hamming distance. Again, the entropy is low. We don't know how to attack it at all. Techniques don't seem to apply. And L infinity, just pick it out of the hat. Just things which don't seem to work. The technique just falls apart. Our technique requires us to be able to subtract the contributions basically for the bits that we know about in order to give the contributions the bit we don't know about. But in some distance functions, you just can't do that. That abstraction doesn't exist. So what can we do there? The punchline is there's a huge amount to be done. Thank you very much.